the screen is dark. It's a little challenging to set up. I better not touch it, otherwise it will be worse. So you got this handout, and it will be base for your votes, right? And here is how you decided to present it. So Amelia for 1, John for 2. I miss
yeah,
spelled.
there's a typo there.
Youngyo.
That's right.
Okay. Youngyo will be 3, Alyssa 4. And this one looks like the shortest, but it doesn't mean that it is shortest in presenting.
Okay.
You took my words literally and practiced path of least resistance or least action. Okay, Morgan, Kristen. And there is a 7th person who is registered. If he pops up, I send an email. He will do something on linear algebra. I don't know if he will do it. When should come to class at the day of selections? So it is your favorite equation, right? So Hamiltonian, it will be wave function, which is like wave. It's complex time derivative on constant, and here is the total energy operator that eventually we will put in the potential energy. Note that it is time dependent. It does depend on time, and it is a true actual Schrodinger equation. But if we will go into practical aspects of solving this equation, there is a simplified version where time dependence is removed. In some sense, by the end of this meeting, we will become acquainted with simplified version of Schrodinger equation where time is removed. I'm just talking about time and decided to watch part and last time you were not complaining and objecting the concept of commutation, right? So 2 linear operators or 2 differential operators can be swapped with their order only with some penalty. Right? We did an example of applying derivative to a function, and then we see that if you swap the order, the price will be like some non-zero unity operator in this case, and in for other operators it could be something more complicated. There is one concept we missed there, but we will return to it again and again. It's rather simple, and it is one of the postulates, and we will recognize which one. So this equation is a bridge between our abstract mathematical modeling of the universe and actual experiments. So if we will practice actual physical chemistry, if we just predict outcomes of experiments, this will be our favorite experiment. So the Schrodinger equation does predict wave function, right? And each point of space and each point of time. But there are no instruments that measure wave function. Instruments measure color, intensity, what other NMR spectra, right? You can imagine different sets of. And for each measurement, for each instrument, there is an observable. And in some sense, the goal of physical chemistry is to predict the value of observable that will come out of the instrument. So in order to find this value, one needs to construct differential operator that will correspond to this observable and convolute it with wave function according to this little prescription. And we will be returning to it again and again. It's just a little heads up. And it's a little chart that you have already seen, right? How to construct Hamiltonian out of different stuff. So what do we expect by the end of this meeting, if everything goes favorably? So this is equation that you like, or we have to. And it looks simple, but because of the Hamiltonian operator will include a lot of differential operators, it can be challenging to solve. There is a little simplification, a trick that helps to remove time dependence. And then instead of wave function psi that depends on x and t, there will be wave function phi that depends only on x. And then it will be only Hamiltonian and energy. So it is something that those who practice computational chemistry solve all the time, right? You find eigenstates of your Hamiltonian energies of orbitals and orbitals themselves. So we need to follow the procedure how to go from time dependent to time independent, and then we need to acquire a new concept. Well, for some of us it will be new. For some of you may have already practiced it. So the new concept will be concept of eigenvalue problem. Please give me a little sign if you ever heard or practiced. Okay, that's good. That's good. So in some in very narrow sense, the goal of the physical chemistry and quantum theory is to solve this equation, which has multiple solutions, and we need to find a set of energies and a set of orbitals. Right? So that equations like that have more than one solution. And if we get through this concept, then we are in charge. We are ready to work. Okay. So here is our time dependent equation. In this differential equation, partial derivatives, you'll see that this Hamiltonian typically includes derivatives over position in different powers. But with very rare exceptions, the Hamiltonian doesn't include products of derivatives over time and space. So time and space operators are only added together but not subtracted. And in such case, there is a mathematical trick of separation of variables. So it's not absolutely general. In some cases, there are nonlinear equations when it is not applicable. But we are going to assume that our solution can be factorized on the parts that depend only on time and only on space. So we are not in a math class, so we are not going to prove stuff like that. So we just assume that our equation is good and it can be solved by simple approaches. So now if we assume this factorization, we may want to plug it into everywhere we see psi symbol and see what happens. Okay? Please tell me to speed up or slow down because I doubt very much that this one will be recorded. So we are plugging in product of these functions of different variables in place of psi. And then left part will be derivative over time of the product. And what do we do with derivative of a product? Product rule, right? So it will be derivative of first times untouched second, first times product of the first. If our capital X, uppercase X function depends only on position, what will be derivative over time? Yes, in respect to time it is constant, so this term disappears. And this little box hides just this part, minus I OH bar Hamiltonian times T times X. Oh, maybe blind. Yes. So it's a touch screen without blind touch screen.
Is there something behind the
Yes.
camera?
Yes, behind the camera there is minus I H over H capital T capital X. I feel a little better, so I can do something. And then, since the second term disappears, our Schrodinger equation looks this way. So we do have a tactical goal to get rid of the T capital part, to get rid of the time dependence. And we do observe that in left and right, we do have this derivative and function itself. Typically, Hamiltonian doesn't have any time dependence, so we can swap them without any penalty. Maybe T. And if it's just a wishful letter to Santa Claus, like, I wish I can cancel this derivative here and this T here, which could be possible if T will be constructed of a function which is equal to its own derivative. Exactly, yes. You see, everything is set up. You see, yes, it is exponential. So why don't we try to assume that it will be exponential, maybe with some prefactor, and then we will plug it into here and there and see what happens. So on the right part, there will be nothing interesting. It will be just exponential to the power CT. Even if it is covered by camera, you know what it is. On the right, derivative of exponential brings the prefactor to the front. Right? Then the exponential here and exponential, which you do not see, but it will be there, will be cancelled. So we will cancel time dependence. And then on the left part, there will be minus I over h bar Hamiltonian operator and x. And on the right, it will be this prefactor for time-dependent exponential times x. I'll try to write c times x equals minus I over h bar, which, or under x, we understand that it is function of position. X capital depends on x over here. And c is a constant. So what is the dimension of this constant? Are we happy with dimensions? Are you happy with dimensions? I'm not. It's everything correct things should be beautiful, and it looks Hamiltonian is energy, Planck is energy times time, so it will be 1 over time. But if we multiply left and right part by this factor, then it looks much better. Then dimension of this constant times these factors will be energy. I see some skeptical looks.
Oh, it wasn't that. I guess I was just wondering why the X is not canceled.
Huh?
Why don't the X's cancel?
Yeah, please discuss with this.
Oh, okay. Got it.
So like H is a combination of derivatives and some crazy differential stuff. And X is unknown function. And we cannot cancel it before we practice acting with all differential operators on X. If we want to be very rigorous, so some people put little, I need only one, little hat on the top of a differential operator and put the dependence on explicit dependence on a variable after a known function. So I remember that there is like 30 crazy slides that I do not remember why I need them. So I will watch them together with you, but likely we do not need them. Let's do a little summary what we have. By assuming the factorization of a wave function, and by first and second, by assuming that time factor of the wave function has exponential form, we were able to remove time dependence completely. Now our Schrödinger equation has a form of differential operator times unknown function that depends on position only, and a constant that has dimensionality of energy times unknown function. And that's it. This is main thing. Now, the question is how to solve equations like this. So if we practice, when we first got acquainted with concept of equations in maybe primary school, we have like 2x equals 6. And then we get only one answer, x equals 3, right? So one equation, one answer. But if even in algebraic form, if you have linear algebra, for one matrix equation, there is one answer. But this is so-called eigenvalue problem, which means by acting on operator, and later on we will see it can be also a matrix, on a function, which can be a vector, we get the same function with precision of absolute constant. So equations like this typically have more than one solution. And it is a major challenge in any applied math problems to solve equations like this. Like typically all engineering problems are reduced to eigenvalue problem, and then there are specific subroutines on supercomputers that solve it. But equations like this have more than one solution. And therefore, those of you who practice computational chemistry use different approximations like DFT to find set of energies and set of orbitals. From just common sense, when you're considering hydrogen atom and SPD orbitals, those are different wave functions, and they have different energies, right? So in some sense, by going through this course, we will be able to reproduce stuff that you got in freshman chemistry or in high school about this SPD orbitals. Those are solutions of this equation. I'm going to jump through slides which may have some. Okay, we got this. We got this. And we did agree that acting by Hamiltonian on a known function. Sometimes people call it with Greek 5. And then by combining this concept of calling it energy, we get a Schrodinger equation. So nothing new here. Nothing new here. Who was studying German? Who was exposed to German? So what does eigen mean? So if you look into a wiki dictionary, it will be like own, proper, that belongs to something. So the eigenvalue problem means the functions will be own functions, functions that belong to this operator. Because this operator loves this function so much, by acting on them, it doesn't change, just accumulates factor. Generally, by acting by differential operator on a function, it changes shape. And there are several preferred functions that are not being changed by this operator. And there is a large but limited number of such functions. Okay, so we will need to solve Schrodinger equation, which time independent Schrodinger equation. This is an eigenvalue problem. Some of you are already acquainted with it, and it is really good. But for some of you, it could be first experience. I suggest that we approach concept of eigenvalue problems a little slower, looking from maybe the simplest possible example. So I'm going to suggest to look onto reverse engineering problem, so to say. You know, like if there are countries that compete economically, and one country gets some development, some maybe machine, some flying device, and another country wants to compete and get it quicker. Sometimes it's instead of designing from scratch, it's better to look on the working example and try to come back for principles that will help to produce it. So we are going to look onto specific function, and then from a function to reconstruct an eigenvalue problem that you would generate such function, just to get a little more hands-on. Hands. So our goal is to solve Schrodinger equation for eigenvalues, eigenfunctions of energy operator. But the example that we will spend whatever 15 minutes, next 15 minutes will be momentum operator. So we will do some reverse engineering, and we will look on a function that later on will be found to be eigenfunction of similar equation for momentum. Okay, we just eigen on. So I have several replicas of this slide in different level of calligraphy, but we did agree that wave function can be thought as action in the power of exponential. So if we are removing dependence of time And if you are looking, for example, to trajectory, we remember that action was of the same dimension as angular momentum, and same dimension as momentum times position. Okay? You do not catch me on cheating there. So position times momentum times position in the power of exponential will give something that will look like wave function. So if we generally put value of momentum as constant and position as an argument, it will be a function that will depend only on position on one hand. And on another hand, it will be something realistic that will correspond to some situation of wave function in certain conditions. So what is such function? By Euler equation, it will be summation of a sign and imaginary sign. So it will have real and imaginary projections, and there will be oscillations. So a sign starts from 1 and then goes to 0 and to negative. So this one is real. And sine starts from 0 and then goes up, right? And if we combine these two projections together, like red line and blue line together, it will be a spiral that coils forward, right? So it's a little unhealthy for brain sanity to imagine things like that, but for simplest example, it is okay. So example of a wave function is complex number that coils forward. Okay. So in these coils, one can identify that it looks like a spring, right? And the coils of the spring repeat themselves with a certain spatial period, right? So after going a little bit forward in space, the pattern of the spring will repeat. And as scientists, we want to measure and give name to this period. We can call it this Greek letter lambda and tell that it is a period, spatial period of wavelengths. How soon the coil will reproduce itself. So our goal is to bring certainty in all these names and concepts and reconstruct the equation that will generate this function. Because the function looks nice to us. It looks in agreement to our general philosophical thoughts about how time-independent wave functions should look like. So you should generate an equation that will produce this function. Skip several slides because we simply do the same stuff. Okay, same thing. A period, a coil. Now, let's do a little experiment, mathematical experiment. I'm not sure if you will do a real experiment in this class ever, but mathematical experiments are fun. So let's take this function and apply spatial derivative to it and see what happens. So derivative over space of exponential will be exponential again, right? And everything except independent variable will pop up as a factor in front. Okay? So on the left you have ddx of exponential. On the right, you have IP over h bar times this exponential. So if we remember, as at the end of the previous class, we canceled function to go to symbolic notations. So we know that function is there, but in some sense we can cancel it just symbolically, algebraically, and then derivative over position is equal to imaginary unit times momentum divided by Planck constant. Or if we multiply left and right by Planck constant and minus I, which is equivalent to divide by I, it will be that imaginary unit times Planck constant times derivative over position is equal to momentum. Remember this little table of conversion of variables, classical variables into operators. If you look into this table, you will see that it is first record or maybe second record in this dictionary. So anywhere we see momentum, we need to replace it by minus IH bar and derivative over position. So and I'm always forgetting that there is a custom to put a little head to highlight that it is operator rather than a variable. And operator means that we assume that there is empty spot after this operator where we should plug known or unknown wave function. So when we write equations like this boxed equation, it's not a literal explicit thing. It's a symbolic representation of operator which cannot exist itself. It's always, we assume that this operator acts on a function. So there is something after this operator, after this construction, same as it was here. Good? Make sense? Now, we can look on this stuff from different angles. If we would put an unknown function phi here and a known function phi there, right? Then we will have the operator acting on a known function equal value of momentum acting on a known function. So we can consider this as a eigen function equation that will generate these exponentials as a solution. Okay? This little experiment doesn't give us general protocol for solving equations like this, but through this reverse engineering, first we just looked on a function, looked on its properties, and then we reconstructed an equation that would give such function as a solution. And you notice that by selecting different value of momentum here and there, you'll get a function with different density of fringes, with different wavelength. And by the way, the name of this function is plane wave. Why plane? Because everything in the real world is three-dimensional, but this is one-dimensional. So we assume that in two other dimensions, nothing is changed. Everything is like a plane. And in the only direction that we explore, things are oscillating. So operator of momentum acting on the unknown function gives eigenvalue of momentum acting on the unknown function. And by solving this equation, we will get set of plane waves and set of values of momentum. Here, they will change continuously. So for any value of positive or negative momentum, there is a plane wave with dense or sparse fringes. little play with, yeah, we're perfect in time. A little play with dimensions. If we take our spring, our coil that we imagine in our heads, and try to write an equation for it from scratch. So it will be 2 angle. Angle should be argument of the exponential, same as for Schroedinger. And it will be 2 pi, and then how far we get forward divided by the wavelength, right? Spatial period. So if it is 1 period, it will be 1 coil. 2 periods, 2 coils, 2 revolutions on one hand. On another hand, it is like action, which is momentum times position. So if we compare these 2 things, if we identify that in both expressions we do have something multiplied by position, right? And this something, which is in circles, should be equal. I missed the P. Here should be P. Yes. I P over H bar equals I 2 pi over lambda. And if we cancel imaginary units and multiply everything by H bar, there will be relation between, so this is not operator, this is eigenvalue of momentum for a plane wave in connection to the period. So period is spatial offset between coils. And they are in the inverse relation. The denser the coils, the larger the momentum. The sparser the coils, the smaller the momentum. Oh, it is written here. Momentum is inverse of the wavelength. Good. I'm in agreement with myself. So we do not have enough practical protocols to solve all problems, but we are getting more hands-on knowledge about how solutions, how wave functions equations should look like, and how they relate to operators and other equations. So this, it's just a little summary. Operator, unknown eigenfunction, eigenvalue. We are solving equations like that. In this example, our operator was momentum, but for most cases, we will be solving operations like this for the operator of energy. So operator of energy acting on the unknown function will generate the same function times eigenvalue of energy. And equations, eigenvalue equations have more than one solution. So we need a list of eigenenergies and a list of eigenfunctions. In a narrow sense, if you can solve such equation for different potentials, for different circumstances, you are done with physical chemistry and quantum theory. In broader sense, of course, we want connection to experiment and observables. Our favorite slide. Thanks for attention. Meeting is dismissed. No lab this week again. Just accumulate thanks. Send me emails if you need more materials or if you have draft of your presentation for Monday and you want me to read it. Also, I would appreciate if you send all final versions of slides by Sunday midnight. So I'm going to print and upload them to the computer so that we do not waste time on putting memory stick, or if the screen is not working, so we still can. Done?
I didn't talk to your clients. And all it is just a summary. You just put it in the book. It's just, you have a book, right?
Like a
Lab book?
copy, like a coffee copy.
You don't, I don't
I
think
do
it has to
have,
be a
but
carbon copy.
I still feel like
I don't know if she'll care or not. She might just, she might, yeah, she might want you to like copy it into your book, but anyways. Well, yeah, but in the syllabus, get a laptop, like, but, yeah, I mean, I don't know, she seems pretty relaxed, so I don't know if she'll care.
Yeah.
So, yeah, that's all I did, it's just like the procedure thing.
Yeah, that's it. Like, she mentioned inclusion, but there were no inclusion.
There's no equations and also there's no,
Yeah.
so there's no need to have either of those. So, and
She
it's
would've
her
said
first
that.
time teaching it, so obviously I think I don't think she cares too much.
No.
She's
Yep.
just kind of trying to get through it.
Yeah.
So,
Thank you.
Thank you.
Can I have a question?
Please.
Can you send me an email about like previous slides?
Oh,
Or is
from
that-
previous years.
Yeah.
Oh,
I mean,
you're
no,
looking
no.
for inspection path. It's okay. Yes, I'll try to do it. Please send me a reminder
Yeah.
if you do not see it soon. I
It's
wanted to send it to everyone
Thank you.
so that you feel.
Some points make me confused, so I don't want to repeat that. So yeah, that's.
Mhm.
Thank you. And I'm sorry about that, but is our homeworks gonna be like a programming or coding kind of thing, or problem solving?
It will be both.
Okay.
Problem I don't know how to articulate and verbalize it, but formally, in this course, I have rights only to assign problem solving. But I will give such hard assignments that everyone will